Today's actual lesson. I've gotten a couple questions about this kidney-shaped pool. How do you find the midpoint estimate with the midpoint rule thing, area? Okay, so what I should have made more clear is that you don't have to extrapolate any values. As in, you don't have to estimate midpoints, just use things you're given as midpoints. So the idea is you could estimate this area by making boxes. Like this would be your first box. This would be your second box. Sorry, that would be your next box. And this would be your last box. Do you see what I mean by that? And you use 6.2, 6.8, I think that's 5.0 and 4.8 for the heights of your boxes. How wide is every box?
4 meters.
4, I think.
It'd be 4, yeah.
Is 4, because it was 2 meter intervals, right? You did 2 meter intervals.
So,
Yeah, so n is 4. I think your change of x officially is, yeah, your delta x would be 4 in that case. But the thing is, they did delta x equal to 2, and so if I had asked you like about left endpoints, you totally could have used like the values themselves, but I don't want you to actually extrapolate anything. Yeah.
Well, wouldn't it also work if the delta x equals 2 if it's like if you did just do half like that would be 3.40 between 0 and 6.2 or no 3.1.
It's just going to make the TA's life hard to grade multiple different right answers. Does that make sense? It would work, but you have to guess something as opposed to using the number that you're given. So let's just stick with 4 boxes just to be consistent. But I really should have put it in the directions. And that really was your textbooks. I took that problem directly out of your textbook, and it didn't put it in the directions either. So it's just kind of like bad design on their part that propagated to bad design on my part. So just use n equals 4, do 4 boxes. And they almost always want you to do that when you see stuff where they actually give you values. They almost never want you to guess a thing in the middle. It's kind of like getting values in a table. They almost never have you guess a value in the middle. They just have you use values in the table and do fewer intervals for the midpoint rule, like fewer pieces. So
which values are you using for the midpoint?
well, if you draw those boxes, it'll be in the middle one.
The middle one?
Yeah. Yeah, so draw the boxes, and the middle one is the thing you take to be like the height of the box, and the width will be consistently 4. Okay. So moving to disk method stuff. So in general, the volume of a solid was given by an integral from A to B, area of a cross-section dx, right? If you were looking at the x-axis, if it was the y-axis, it was dy. What if you have a rotational thing? What if it's a spinny thing? What are your cross-sections then? Uh-huh. The volume will be the integral from A to B, pi r out squared minus r in squared. If you don't have an r in, that r in is just 0, then it's just pi r squared. So we're going to use that to set up a bunch of integrals. So first, how about we sketch the graph of the region bounded by y equals x squared and y equals 2x. Set up, but don't solve. Like on your take-home, on your quiz, there's going to be like this thing in bold. You don't get extra credit for solving when I ask you not to, okay? It doesn't work that way. You just waste your time. So follow directions. Okay, so y equals x squared and y equals 2x. Goes through 0, 0, 1, 1, 2, 4, right? So where does y equals 2x start? The origin. And then it rises 2, runs 1. So that's the thing we're rotating. And for this first problem, what are we spinning it around? X-axis. Okay. So when you spin that, will the outside be straight or curved? Straight, inside's going to be curved. Which curve is the outer curve relative to the x-axis. So our out is y equals 2x, or just 2x. Our in is which one? X squared. So in this case, the volume is equal to pi integral. Ooh. Do you use x values for those bounds, or do you use y values for those bounds? X values, because you're talking about the integral in terms of x. You also can think that if you're thinking back to slices, your slices have dx's, so it's where they start to where they end. So what is this x value where they begin? 0. What is the x value where they end? 2. And then we'll have 2x squared minus x squared squared. And that's really it. You can stop there.
You do on the homework ask us to simplify.
I do on the homework ask you to simplify the integrand, so let's do that as well. I think the take-home on the in-class quiz I did not. But simplifying the integrand, what I just mean is square appropriate things and combine like terms. So what is 2x, the quantity squared? 4x squared. And how about x squared squared? X to the 4th.
So unless you specify to simplify, all we actually have to do is that first.
Yep, and I think I'll even specify that you don't need to simplify your integrand to be extra careful. But yeah, in general, if I just say set up, don't solve there, but in the quiz I just wanted you to actually do the little bit of algebra to make sure that you could do that right as well. Does that make sense? Okay. So there's the x-axis. So same picture. So I've got to redraw it. Y equals 2x and x squared. So it looks roughly like this. Okay. So what if I spin around the y-axis now? Do I slice vertically or horizontally? Horizontally. Okay. Now what's at least one thing that's changed? The outside is now the curved one, right? The inside is the straight one. If you're going to slice horizontally, instead of having the curves as y equals stuff, you're going to have them as x equals stuff. Yep. So the parabola becomes x equals root y. And it's positive root y because we have the right half of the parabola. What does the line become? Y halves, yep. 1/2 y or y over 2.
And you change the bounds to 0 before, right?
Exactly, yep. Your bounds should also have y's in them. So your volume is still pi integral r out squared minus r in squared. It's just the difference is now we're dy, and usually your book will say c to d, where c and d are y values.
So is root y r out?
Root y is your out. Do you guys agree? Yep. So root y squared minus r in, which is
The other one?
y over 2 squared. And then the bounds. You need to think, where do my slices start? Where do they end? They end at a y value of, they begin at a y value of 0. They end at a y value of 4. And because I asked for it on the take-home quiz, let's just go ahead and simplify that slightly. Root y squared just makes y, and then y over 2, the whole thing squared is
Y squared over 4?
great. Yep. What I mean by simplify is kind of get to the stage at which you would do antiderivatives, right? Gesundheit. Okay, y equals -5. So first of all, is that a horizontal line or a vertical line? Horizontal line. Okay, so there's y equals -5, or the parabola. Here's the line. Okay, so y equals -5 is a horizontal line down 5. So is this more like the x-axis spin or more like the y-axis spin? More like x, do you agree with that? Okay, so kind of like the x-axis, which I think, do you agree, means you're going to use x values just like you do with the x-axis rotation? Yeah? Okay. So we slice like this. Which curve is outer, purple or black? Purple is. Okay, so to get all the way to that outer curve, you first have to go up to the x-axis. How far is that? 5. And then out to the purple curve, which is 2x. So r out is 5 plus 2x, or 2x plus 5, right? R in is the distance from the axis of rotation to the inner curve. So what's that going to be? 5 plus x squared, or x squared plus 5?
So it's not gonna change anything if we just call it 5 minus minus. 'Cause
No, if you call it 5 minus minus, it won't change anything. No, but you should just say plus. Because the double negative is what makes it positive, right? Okay, and then what are the bounds on your integral? 0 to 2. Okay, so our outer curve is 2x plus 5 squared minus inner curve, which is x squared plus 5 squared. And let's just go ahead and expand that because it wouldn't hurt. If you square 2x plus 5, we get 4x squared plus how many x's in the middle? 4x times 5, so I think it will be 20x. Do you guys agree with that? Plus 25 minus x to the 4th plus how many x squareds? 10 plus 25. And you can combine some like terms, right? 25's cancel. You also can combine these x squareds and those x squareds, right? So we'll end up with 20x minus 6x squared minus x to the 4th. Does everybody agree with that? Because I sometimes add bad. Is that all right? So take-home quiz, we definitely want this. In-class quiz, this is where you can stop. Does that make sense? Okay. All right, one more. Did a horizontal line, now we're going to do a vertical line. Okay, so parabola. Okay, x equals 10 is somewhere way out here, right? I mean, that's not exactly right, but you know, that's where it is. Do you agree? Okay. So is this more like the x-axis or more like the y-axis? More like y again, right? Okay, so we're going to slice this way. So who's my outer curve? The line or the parabola? The line. If you go from this axis and go out, the furthest away one is the line, right? So that line, once again, was x equals y over 2, and the parabola was x equals root y. Okay. Okay, color coding. So this whole distance, really thick, from there to there is how far? 10, okay? When you measure that y over 2, that's the distance from there to there is y over 2. Does that make sense? The distance that you want is from here to here. Okay? 10 minus y over 2.
wouldn't it be negative 10 plus y over 2? Because you're going left.
It would be both.
So well, I can't process. Just let me write down what I have. So r out is definitely So what did you say it should be?
Negative 10 plus y over 2.
My only concern is that's definitely going to give you a negative number. But you square it, so it might end up being the same thing in the end. I'm not sure if that'll consistently work.
But you're going left with your 10. So
I don't think that that's the way to think about it. I think that's actually the wrong way to think about it. I think the way to think about it is, what is this distance? It's not, am I going left or am I going right? It's how far is this as a like positive number.
Oh, okay.
So I think that it's just like probably just not the greatest way to think about it. That's all. What would Rn be? 10 minus root y. Okay, what are your bounds? 0 to 4. 10 minus y over 2 squared minus 10 minus root y squared. Y. Oh man, I said I'd simplify, so there you go. Okay, so it's going to be 100 minus. Do you guys agree with the 10y? The trick is you do this number times 2, right? Okay, and then plus y squared over 4 minus 100 minus how many root y's? And then plus y. You got y squared over 4. I think minus 11y. Do you agree with that? And then plus 20 root y. Is that right? Yes, no? Look good? Okay. There may or may not be a take-home quiz question like that, right? Okay, some kind of similar. All right, this time we're actually going to a volume. So we've done a lot of things that your book has lots of stuff that's polynomials, but also it's good to know how to do things with other functions. So how about e to the x? So rotate e to the x bounded by y equals 0, x equals -1, x equals +1 about the x-axis. So first, sketch a little picture. What's one nice point e to the x goes through? 0, 1. Yep, so that's 1. And when you're at 1, e to the 1 is just 2.71. So approximately up there someplace. What happens as you go to the left side of that 0, 1 point? What is the e to the x approach? Goes towards 0. So you're rotating this region about this axis. Does this solid have a hole in it? No, it's actually a solid, right? Solid. So the area of a cross section is just pi r squared. What happens to be your r in this case? How far is it from there to your axis of rotation? There to your axis of rotation. E to the x, yep. So your cross section's area is pi e to the x squared. Ooh, what happens when you raise a power to a power? Does exponents multiply, or do they add? Do they exponentiate? They multiply, so that becomes pi e to the 2x. Think about an easy example, like x squared to the 5th. You get x squared 5 times, that's 10 x's, right? Multiply. All right, so your volume is pi integral e to the 2x. What are the bounds? And is that an integral you can do pretty easily? Yes. So it'd be pi over 2 e to the 2x. So pi over 2 e squared minus e to the negative 2. And you can maybe do stuff with that, but that's good enough.
Was it possible to do something where you rotated on the y-axis and kind of rotated the cell?
Yeah, I've never seen an example do something like that unless I did it by accident. So, no. You just stretching, Zach?
Yeah.
Okay, awesome. So these were the solids where we had rotations. We also had examples of solids where cross sections were different stuff, right? Like squares or equilateral triangles. So in that case, your answers have pi's in them?
No.
No spinning, no pi. No spinning, no pi. Don't put pi there if there's no spinning. You're going to get partial credit for not having pi. All right, so we have a region S who's enclosed by the parabola 1 minus x squared. That's his base. So there's 1 intersects at negative 1 and 1. And that's the base of the region. Set up an integral that finds the volume of the solid if the cross sections are squares that are perpendicular to the, in this case, x-axis. You slice like this, and what comes out at you are squares. So where is this thing going to be biggest?
Right in the center.
In the center, it's going to decrease on the ends. It looks a bit like a sand dune when you look at it. Okay. So the area of a cross section is given by side squared. In this case, what is my side? What function? 1 minus x squared. Squared. So your volume, without using any symmetry trickery yet, is an integral from where to where? And of just that 1 minus x squared squared thing. There's no pi there because you're adding up areas of squares, not areas of circles. Could you, if you had to actually do it, could you use symmetry to make it easier? Yeah, you could say instead twice integral from 0 to 1, 1 minus x squared squared. Okay, so if you're perpendicular to the x-axis, you're going to use x. It's kind of like rotations around the x-axis. You also use x's, right? The next one's a teensy bit different because, same, but you're going to slice the other way. Okay, so now you're going to slice this way. So whereas the previous one had this sort of like symmetry where it was biggest in the middle, this one's going to be biggest on the far end along the x-axis. And then it's going to just kind of, the squares decrease in size as they get closer to y equals 1. Oh, goodness. Okay. Since you're slicing horizontally, what do you need to solve for to find the length of that side? You say solve for x, right? So you have y equals 1 minus x squared. So that's the same thing as y minus 1 equals negative x squared, right? Or 1 minus y equals positive x squared, right? You buy that? So technically x equals plus or minus the square root of 1 minus y. Which part of that parabola does the plus half give you? The right half. So top relative to the y-axis. And the negative part gives you the left half. Okay. All right. So your area is still side squared. But what is the side this time? Is it just root 1 minus y? It'd be 2 of them, exactly. Because root 1 minus y just tells you the distance from the y-axis over, just that part. And there is symmetry, so you can say, okay, well, it's just twice that much. In the previous problem, your bounds were x values. Now, because you're slicing horizontally, they're y, so that'd be 0 to 1, 2 root 1 minus y quantity squared dy. Which would simplify quite nicely, wouldn't it? It'd be 4 times 1 minus y. That maybe was a homework question. Was that question asked in WebAssign?
That's on the table.
It's on take-home? Oh, look at that. You better all get it right now.
We have to solve.
You have to solve it, though. Oh, no. Okay. It's kind of a gimme. Now it's gimme. Okay. Now, all of the next examples that we have, they're going to use fancier integration techniques from Chapter 7. So we're going to set the integral, figure out which technique to apply, and then we're going to do it. This is one problem with doing this unit after doing fancy integration techniques, is you forget those fancy integration techniques unless I bring back problems that use them. Okay, so here we go. So find the volume obtained by rotating the region bounded by y equals sine squared of x about the x-axis.
Oh God, I don't know what that graph looks like.
And neither do I, but you can kind of guess. I mean, for stuff like this, you can also look it up, but let's just first graph sine of x. Sine of x looks like this. That's right, regular sine. You buy that? Okay, and this highest value there is 1, right? So if you square everything, all these positive values, you know, they stay positive. That one value stays one. Their values change a little bit, but the kicker is they all stay positive. What happens to this part down here? It's going to flip, and it's going to have some sort of the same exact shape as the previous bit, right? This is not an exact graph, but roughly speaking, that's what this thing's going to look like, right? So we're taking this region, and we're spinning it about this axis, and only up until pi. But they could have gone to 2 pi, would have been fine. And for stuff like this that's strange, if you have to use like Wolfram Alpha or something to graph it, go ahead and do so. It's totally fine. Usually for super weird stuff like this, they'll give you a picture, like on the quiz. And your book does that for some homework problems as well. Okay. All right. So the area of a cross-section is pi r squared, right? This one doesn't have any holes in it. What is our radius this time? Sine squared of x. So you've got sine squared of x squared. And other than the presence of the 0 and the pi out in front, you did stuff like that in the last chapter, didn't you? When you have even powers, what identity do you have to use? The half angles, exactly. So that's pi integral 0 to pi. This sine squared becomes 1/2. 1 minus cosine of 2x. Great, the whole thing squared. Then square everything, as in expand. So that 1/2 becomes 1/4. Let's make it pi over 4. Integral 0 to pi, that'd be 1 minus 2 cosine of 2x plus cosine squared of 2x. Minus 2 cosine 2x. How about cosine squared 2x? What's that become? 1/2. 1 plus cosine 4x. Okay, so finally, before integrating, I'm going to combine like terms. They'll give us 3/2 minus 2 cosine of 2x plus 1/2 cosine of 4x. Everyone okay with that? When do you use the formula that is 2 sine x cosine x? What is that associated with? Sine squared? Yeah. Okay. So what's the antiderivative of 3/2? 3/2 x. How about -2 cosine 2x? Negative sine 2x. Do you guys agree with that? Because sine's derivative is cosine, 2x's derivative is 2, right? And this one, what's its coefficient going to be? 1/8 sine of 4x. And actually, this is a pretty nice one. We're just going to have pi over 4, 3 over 2 pi. When you plug pi into this guy, you get sine of 2 pi, which is 0. You plug pi in that guy, you get sine of 4 pi, which is 0. What about when you plug 0 into all the remaining functions? All zeros. So we end up with 3 pi squared over 8. Wasn't so bad, right? Just a little tedious. I could ask you to find the area, the volume generated by rotating sine x around the x-axis the same way, right? That'd give you sine of x squared or sine squared x. Just be one application of that half-angle identity.
If this is a good one, what are the bad ones look like?
Oh, there are no like super awful ones. There is one trig sub. Sorry. Ah. Okay, here's 2 regions. Oh no, in between sine and cosine, between 0 and pi quarters. Ooh, well, the nice thing about this is that there's no switching happening, right? As in, which one's above stays above the whole time. Okay, so let's just graph to pi halves. So sine starts at 0. By pi halves, what's it up at? 1. Okay. Where does cosine start?
1.
Goes down to 0 by pi halves. What is this intersection point right there? Pi over 4. Sine equals cosine at pi fourths. They're both root 2 over 2 there. Oh man, I made it even nastier. It isn't about the x-axis, it's about the line. How dare I? Y equals 1. Oh no, oh no. I made a promise to not only do easy problems in class, and then I regret that promise. I promised myself. I'd not made it verbally aloud. Oh no. Okay. So in that case, who is the outer curve, sine or cosine? Does that make sense? I think that. Write on who's who. It'd be sine. Relative to y equals 1, sine is outside. Do you agree? If we were spinning about the x-axis, then cosine's the outer curve, right? But because we're spinning about the line y equals 1, sine's the outer curve. Okay? Oh no. Okay, 0 to pi quarters are our bounds. We'll have r out squared minus r in squared. So how far is it from y equals 1 to that outer curve? Is it just sine x? It's 1 minus sine x. What's r in going to be? 1 minus cosine x. Oh, goodness. I do 1 minus sine x, the quantity squared, what does that make? Plus, great. And then minus the quantity 1 minus 2 cosine x plus cosine squared x. Some semi-nice stuff happens. Only kind of. The ones cancel. You get negative 2 sine x plus 2 cosine x plus sine squared x. And is it minus or plus cosine squared x? And if you're me, I'm angry because I wish it were sine squared plus cosine squared, because I could just say it was 1, right? But it's not, so you can't, right?
Wait, can you break it down and then
Break it down into,
different integrals and then add them up?
yes, you can, but I don't think that's easiest to do until you've simplified the inside of the integral completely. My personal preference is all, but yeah, you could do the first two and then do the next two as well. I just think it's easier to first combine like terms and cancel stuff, less writing, in my opinion. So since you have no other option, how would you deal with sine squared and cosine squared? Half angles again. Yep, exactly. So pi, 0 to pi quarters, minus 2 sine x plus 2 cosine x plus a half 1 minus cosine 2x, and then minus a half, that one's 1 plus cosine 2x. My dx don't fit. I know I missed a parenthesis there.
Can't you just use the cosine double angle to make a negative cosine 2x?
Can't you use the cosine? Yeah, if you knew that one, which I didn't. So the one that you're looking at, there is a formula, and I've just forgotten it. It's that sine squared x minus cosine squared x is equal to 2 cosine 2x.
It's like cosine squared minus sine squared, but it would be negative 2.
Yeah, and so we're gonna put we're gonna get that this way as well. So if you see that right away, yes, you can totally use it. I just don't see it right away. Does that make sense? Yeah, so we will get that and you could use it. So let's talk about how we're gonna use this in just a sec. So pi, 0 to pi quarters, negative 2 sine x plus 2 cosine x. So first of all, what will happen to the 1/2s? You're going to get a positive 1/2 here and a negative 1/2 there, right? They cancel. Do you get that? Okay, then you're going to have a negative 1/2 cosine 2x and another negative 1/2 cosine 2x. So what does that become? Just cosine 2x negative, right? So this identity that you could look up and is totally fine if you have it memorized is, I guess, that cosine squared x minus sine squared x equals cosine 2x. Is that right? So you see how we have the opposite of that? That's why it came out negative. So if you know that, yes, you can use it. But notice that you didn't have to know it. If you just know these half angle ones, you're going to arrive at it at the end. But if you're faster, totally fine. Okay, now can we finally integrate? I don't know why I sounded whiny because I made this problem up. So what's the antiderivative of negative 2 sine x? 2 cosine x. Plus 2 sine x, do you agree? And then plus, minus a half sine of 2x. Zero to pi quarters. Okay, first plug in pi quarters. When you plug pi quarters into cosine, what do you get? Okay, so you got 2 times root 2 over 2, which just gives you root 2. Plug 2 root pi over pi of fourths into sine x, you get root 2 over 2 again. And then plugging it into here, you get sine of pi halves, which is 1, so minus a half. Gesundheit, minus. When you plug 0 into cosine, what do you get? 1, so that's 2. Cosine of 0 is definitely 1. Sine of 0 is 0. Okay, so that's pi times how many root 2's? 2. And you've got negative 1/2 minus 2, so give me a nice improper fraction.
Isn't that an oxymoron?
5, I think it's 5 halves,
Oh,
right?
much better than the next number.
Isn't it an oxymoron to have nice improper fractions? No, it's just not up to elementary school etiquette. But it's not, I know it's not, right?
Ms. Henderson must have a stern talk to you.
Yes, yes, your teacher must have certain talking tos with me. Okay, ready? Next one. You graphed weird stuff like this in Calculus 1. Like when you were asked to use calculus to graph curves, a really common one to give you is something kind of like this. You can figure at least one point that goes through. Plug in 0. What do you get out for the y value? 1. Your favorite number in the world should be 0, right? Is it?
One's pretty easy.
When you plug in 1, you get 9 over 10, which is less than 1, right? So you get a point down here. Do you agree that as the x's get big, this thing's going to go to 0? Do you buy that? So it's going to do this kind of business down to 0. And it does the same thing on that side, because it's an even function. Okay. But once again, if it's super weird stuff like this, I definitely would either give you a graph, or if it's a take-home quiz, I think you can use graphers to like graph it. That's kind of like making sure you can use technology. Okay. So rotate the region enclosed by the curves. Y equals 9 over x squared plus 9. Y equals 0. That's the x-axis, right? X equals 0 is the y-axis, and x equals 3 about the x-axis. So we're spinning this thing. Does this one have a hole in it? No, okay. So the volume is pi integral. What are the bounds on your integral?
0 to 3.
0 to 3. And your radius is that. The whole thing squared. So can I just pull out that 9 squared as an 81
Yep.
and make that 81 integral 0 to 3. Oh, yes, thank you, 81 pi, x squared plus 9 squared. And I need parenthesis. Okay. Ooh, icky, icky. Well, so, you had a question like this on a recitation worksheet, I think, and probably a take-home quiz too, maybe. It's one of those instances where you have to use a trig sub, even though there's no root sign. You can't use partial fractions because this is already like decomposed. So given the hint that you have to use a trig sub, what should your trig sub be? X equals 3, and then which function? Tan theta. Okay, your dx is 3 secant squared theta, and let's just change the bounds because it really, really is so much easier. If x equals 0, we have 0 equals 3 tan theta. At what angle is that true? And at x equals 3, we have 3 equals 3 tan theta, or tan theta equals 1. So what angle does that happen at? Pi over 4. Okay, so 81 pi integral 0 pi over 4. What goes in my numerator? 3 secant squared theta d theta. And the denominator is 9 tan squared theta plus 9 squared. Okay. So there's no square root here, but what does 9 tan squared theta plus 9 simplify to? 9 secant squared specifically. And it's still squared, right? So a couple things happen. First of all, that 9 squared is 81, right? So that can cancel out the other 81. Does that make sense? And out in front, our constants are just going to be 3 and pi. And then I think we have how many secant squareds left and where are they located? Bottom, and there's 2. Okay, well, 1 over secant squared, what does that make? Cosine squared. And the identity just keeps coming back to bite you in the butt, doesn't it? Can't run away from it. So 3 pi over 2. We're almost done. 0 to pi quarters. So cosine squared is... And I already took care of the 1/2 because I put the 3 over 2, right? Okay. So that's 3 pi over 2 times theta plus 1/2 sine 2 theta. When I plug in pi quarters, I get sine of, which is 1. I think Gesundheit. Does plugging in 0 give us 0 in this case? Yeah, okay. So if you want to distribute, which you don't have to do, your answer is 3 pi squared over 8 plus 3 pi over 4. Ugh. So far we've done trigonometric half-angle things, trig sub. Which integration technique are we missing? Your worship part's for the hint that this is the next one's going to use, okay? Go ahead and groan. Oh. Okay, all right. Now that we got that done, let's solve this one. So y equals ln x, y equals 0, x equals 2, about the x-axis. All right, so you have to know a little bit about y equals ln x, what it looks like. So where does y equals ln of x intersect the x-axis? At 1. And it has a vertical asymptote of the y-axis and looks like that-ish. Okay, so y equals 0 tells us one bound is the x-axis. X equals 2 gives us this right bound. And we're going to spin it about the x-axis.
It doesn't sound too easy.
It's not too bad. Okay, so the volume is equal to integral from, where do your slices, well, pi, where do your slices start? 1 to 2, very good. And your radius is ln x. So I asked Marty Getz what he calls these things, because it helps to have integrals that have names, so you can remember what they are. He calls these guys the loners, because there's only a function inside of the integrand. This is not a great example. What he was referring to was stuff like the integral of, well, we had arc sine of 5x or something like that. There's like one. It's a way to refer to that trick where you have to let dx be part of the thing you're working with. Does that make sense? So your only option here, and I don't know, can you integrate ln of x easily? Is the integral of ln of x 1 over x? No, that's the wrong direction. So the only thing to do is to let u equal the whole ln of x squared, which means what's left over to be your dv? Just dx. Okay, so v is equal to x. It's easy enough. du, oh, you cannot forget that chain rule from calculus 1. 2 ln x times 1 over x. Okay. So pi times uv, so that's x ln of x squared. That part from 1 to 2, because it's already integrated, minus, what do I get when I multiply my v and my du? To, I think it's just integral ln of x. Do you guys agree? Okay. So that's number 1. Okay, here we have pi times 2 ln of 2 squared minus 1 ln of 1 squared. But what is ln of 1? 0. So can I just erase it so I have more space? Okay. I'll just say minus 0 to make it pretty clear that that was a 0 term. Okay. Now, how do you integrate ln x dx? We did actually do it in a previous problem, but my guess is most of you forgot it. Yeah.
Isn't it x ln x minus x?
Ooh, great. It's x ln x minus x. To prove that, you do integration by parts again. Does that make sense? Same trick. You let u equal ln x, du is 1 over x dx, dv is dx, v is equal to x. But just in the interest of time, let's just go with, since we knew what it was, from 1 to 2. Okay, just be really careful with negative signs. Pi 2 ln 2 squared minus 2 times 2 ln 2 minus 2 minus 1 ln 1 minus 1. Do you see what I mean about negative signs? Okay. So you have pi times 2 ln 2 squared minus 4 natural log of 2. Okay, when I do this negative 2 minus a negative 1, I get negative 1. Multiplied by this negative 2 gives me plus 2. And I don't know, my ln n looks like an n when that should be a 2 inside. So 4 ln 2 plus 2. That technically, okay, yeah, so good, done. Lots easier. You okay with that? It's just tricky. These definite integrals just get kind of gross quickly. Last one. This is kind of cool. This is a special thing called Gabriel's horn. So you take the curve, and it's an example of a solid that has finite volume but infinite surface area. It's real strange. Okay, right. You understand when I said finite volume, which means the volume is finite but its surface area is infinite. Is that a little weird? Yeah, slightly, okay. But we can at least, now, we can prove that this is a finite volume. So what does 1 over x look like? Like, sketch it in the air. Yes, but, right? Goes through 1, 1, and then it decreases to 0. And we only care about the interval from 1 to infinity. So from 1 to infinity. If you find the area under that curve, it's actually infinite. We're finding the volume. So pi. Will this solid have a hole in it? No. Okay. What are the bounds on my integral? 1 to infinity.
Does that create a limit thing?
Yeah, it's going to create a limit thing, yep. So the area of a cross section will be, pi r squared. What is my r in this case? 1 over x. So 1 over x, the quantity squared. So that makes 1 over x squared, right? Okay. So pi integral 1 to infinity 1 over x squared dx. And yes, you do have to do a limit thing with this. So you have pi times the limit as your upper bound goes to infinity, integral from 1 to b, x to the negative 2 dx. But it's a pretty easy example of one of those integrals from section 7-8, right? What's the antiderivative of x to the negative 2? Negative 1 over x. Great. X to the negative 1 over negative 1 makes negative 1 over x. So you have pi, limit b goes to infinity, negative 1 over b plus 1 over 1. So Han, what happens to the 1 over b as b goes to infinity? So this thing goes to pi. So the volume of that solid is pi. Crazy, huh?
Spike in the surface.